We will start today with the BJT differential amplifier or differential pair, which is an implementation of the differential pair that we saw, but now with bipolar transistors instead. So this is the differential amplifier with bipolar instead of MOSFETs. The circuit works almost the same as the MOSFET circuit, with maybe two exceptions, two differences. The first is that in the case of the BJT, we have the base current, which we did not have in the case of the MOSFET. So here we will have some input current at the base. The two inputs are applied at the two bases of Q1 and Q2, and I will have an input current there, which we did not have in the case of the MOSFET differential pair. The second difference is really in the characteristics of the transistor. The MOSFET equation is a second-degree equation. It's a parabola. The BJT equation is an exponential equation. So that's much more nonlinear or powerful or fast. So a little change in the input voltage will cause a large change in the current in the case of the BJT. This is what is really GM, small GM. GM for the BJT is much larger than GM for the MOSFET. So a small change in the input voltage will cause a large change in the collector current as compared to the MOSFET. And this means that for a small change in the input voltage, we may have distortion because the current may increase too much and cause distortion. So these are the two differences. Other than that, the two circuits are very similar. And of course, by just looking at the circuit and with Q1 and Q2 being identical, the circuit has perfect symmetry. So whenever the two input voltages are equal, the same current would flow in the two transistors. And if there is any difference between them, we can show the same way we showed for the MOSFET case, that there will be an output voltage and it will be an amplified version of the input, the difference between the two inputs. And we can take the output from the first collector from here, or from the second collector, or between the two collectors. So just like the MOSFET case. And in many cases, actually, you may see that there is a resistor, RE, that is inserted between the emitter or the two emitters and the common node here. This RE has two purposes. The first is that it will increase the input resistance. And we will see how on the coming slide. So it helps in increasing the input resistance of the amplifier. The second effect of RE is that it will make the characteristics of the BJT more linear. How does it do that? We will study this when we start the topic of feedback. This is a feedback resistor, and negative feedback makes the amplifier characteristics more linear, so we will have reduced distortion. So this is a useful resistor. It will help us in reducing the distortion and increasing the input resistance. But we pay a price, as we'll see later, in reduced gain. And we've seen this when we studied the common emitter with emitter resistor. The effect of a resistor between the emitter and signal ground was that it reduces the gain. So this is a reduction in gain. This is the price we pay, but we get improved input resistance and improved linearity. So if you see this resistor RE, now you know why it's there. And now you know also why we don't typically use it in the MOSFET differential amplifier, because in the case of the MOSFET differential amplifier, the input resistance is infinite anyway. So we don't need to increase it. It's already infinite. And the characteristics of the MOSFET are not as nonlinear as the BJT to linearize them. The parabola is closer to linear than an exponential is. So again, I don't need to linearize and avoid distortion the same way I need to do that with BJT. Okay, let's do now the small signal analysis for the circuit using the T model for the bipolar transistors. Again, the analysis is parallel to what we did for the MOSFET. So this is the first BJT. This is the second BJT. This is the base, the emitter, the collector. This is the second emitter, the second base, and the collector. The supply here becomes signal ground. And the current source that was here becomes an open circuit, because we're assuming now that it's ideal, pure DC. And I'm ignoring small RO for now. So if we do this, we can say that the current here in the first emitter is V pi 1 over RE. V pi 1, because of the symmetry, V pi 1 would be VID over 2. So that's VID over 2RE. And this gives me now IB1, which is IE1 over beta plus 1 and the active region. So this is the input current that we see. The input current is not 0. It is VID over 2 into beta plus 1 RE. And this is a hint to what is the input resistance. IB1 is the input current, VID is the input voltage. And this gives me what we call now the differential input resistance. This is when the input voltage is differential. RID is VID over IB1. IB1 is the input current flowing out of the VID source. So it's 2 into beta plus 1 times small RE, but beta plus 1 times small RE is R pi. So 2 R pi. Not surprising if you consider that the inputs are applied at the two bases, and between the base and signal ground, there is an R pi. The two emitters are at the virtual ground. If I have the RE resistor inserted between the emitter and the common node, which will be at signal ground, then the input resistance for this case, when the input voltage is differential, so that's the differential input resistance, would be 2 into beta plus 1 times RE plus RE. And we see how RE increases the input resistance. For voltage gain, similar to the MOSFET case, we find the collector voltage of Q1 and the collector voltage of Q2, and we get results similar to the MOSFET case. They are 1/2 GMRC. One of them is plus and the other is minus. So at the first collector, it's -1/2 GMRC. At the second collector, it's 1/2 GMRC. And of course, I can take the output voltage between the two collectors and this will give me double the gain. So I can get GMRC without the 1/2, plus or minus, depending on whether I take the plus of the output voltage at the collector 1 or at collector 2. If I have RE inserted between the emitter and the common node, then the gain would be minus alpha RC divided by RE plus RE. And this is almost minus RC over RE plus RE because alpha is very close to 1. If the current source in the amplifier is non-ideal, the results will not change because I will still have a symmetry in the circuit, and we can show that the signal voltage at the common node would be 0. All right, so similar results to the MOSFET case for gain, and we have a result for the differential input resistance, which is 2R pi or 2 into beta plus 1 RE plus RE if I have this RE resistor. What about the common mode gain? Would we have any common mode gain if the two inputs are equal? Do we get an output? This is the half circuit in this case. And I will consider that the current source is non-ideal. Because if the current source is ideal, I will not see any output. If the current source is non-ideal and has an output resistance REE, REE is the output resistance of the current source. Then I can split the circuit into two half circuits due to symmetry. I can do that. The first half circuit is on the left, and the second is on the right. And each will get 2 REE, such that when I rejoin them, the 2 REEs will be in parallel with each other, and their parallel combination would be 2 REE parallel to REE, and that's REE. So this is the half circuit, and I want to find the output here at the collector when the input is at the base, and there is a resistor 2 REE between the emitter and ground. This is the half circuit is a common emitter with emitter resistor equal to 2 REE, and we know that the gain in this case would be minus alpha RC over 2 REE plus small RE. And that's very close to just minus RC over 2 REE. This is the output resistance of a current source, and this is small RE for a BJT. 2 REE would be much, much, much larger than small RE, and we can easily neglect the small RE. So what does this mean? It means that because the current source is non-ideal and has an output resistance equal to REE, if I look at the output at one of the collectors, even if the two inputs are equal, there will be something there. There will be some signal. It will be small, RC over 2 REE, maybe less than 1, much less than 1. So I will see some signal which is smaller than the input, but there is something. It's not exactly 0. The reason is the output resistance of the current source. If it's infinite, if this goes to infinity, the gain would go to 0, and the gain would go to 0, and the output voltage would go to 0. And I can make the output 0 even if I have an REE, and that's by taking the output differentially. So if I consider this to be my output as seen here in the diagram, if this is my output between the two collectors, then the gain will be exactly 0 because the voltage at the two collectors is the same. The difference will be 0, so I get 0 ACM and infinite common mode rejection ratio. For single-ended, if I only take the output at a collector to ground, this is ACM, and I have a formula for AD, and I can get an expression for CMRR. It will be 20 log base 10 of GMREE. So that's the common mode gain and the CMRR. And the common mode gain is not zero when the output is taken from one collector. And the CMRR is not infinite in this case. But the common mode gain can be made zero if the output is taken differentially, or if the current source is ideal and has an infinite output resistance. Here's an example of an implementation of a BJT differential amplifier using NPN and PNP BJTs. So how can we implement such a current source IEE also using bipolar transistors? We can implement it using a current mirror, a simple current mirror. So this IEE can be really a BJT here. And IE would be its collector current. And this BJT would be mirroring another one here that has some reference current flowing in its collector. So this is maybe a golden reference that I have. And I will just mirror it using this Q5. So Q5 would mirror IRF and implement IEE. Okay, so that's how we can implement the IEE using a BJT. Okay, at the circuit, I have the differential pair. So Q1, Q2, no surprises here, just regular differential pair with bipolar. The output is taken differentially between the two collectors with plus at collector 2, minus at collector 1. Okay, what about RC and RC? We don't see RC and RC here. We see PNP, Q3 and Q4. So what's the deal here? What's the idea? The idea is that looking up, instead of seeing just a regular RC, I see the resistance seen looking into the collector of Q3 or the collector of Q4 with their bases at some DC voltage and their emitter also at some DC voltage. So there's no signal here and no signal here. So maybe we should consult the resistor, the formula sheet for resistances. And if we do that, we get the formula for the resistance seen looking into the collector of a BJT, whether NPN or PNP. When there's no signal at the base and no signal at the emitter, we see small RO. That's similar to the MOSFET when we look into the drain with no signal at gate or source. And Q3 and Q4 are supposed to be identical and they're biased at the same current. So RO3 and RO4 would be equal. So instead of using two resistors, RC and RC, RC in this case is RO4 equal to RO3. That's RC. So if you imagine that instead of having Q3 and Q4, you have RC and RC, the circuit would be exactly the same as the circuit that we saw on the previous slides. The question is, what is the voltage gain? Oh no, another one of those questions. What voltage gain? There's something missing here. What is the differential or common mode? Well, just by inspection now, I can answer the question about common mode. Because I am taking the output differentially and the transistors are matched and the circuit is symmetrical, I can say that ACM is 0. Even if the current source is implemented using a BJT, so that's not ideal, ACM would be 0 because I am taking the output differentially. That's easy to answer. So I might as well answer the two questions. What is AD and ACM? We'll get the two. ACM was free. AD, again, I'm taking the output differentially with plus here and minus here. So AD would be from the formula on the previous slide or the slide before it, GM-RC, GM times RC. So which GM and what is RC? GM is GM1, which is equal to GM2. So GM1. And what is RC? RC in this case would be small r of 3 equal to small r of 4, GM1 r of 3. So that's AD. And that's pretty large. For a BJT, GMRO would be quite large. So we have a large, very large differential gain, 0 common mode gain, and of course, infinite CMRR. Oh. Now we will consider a MOSFET differential amplifier. We will also show the BJT version of this, but this is a special kind of differential amplifier. We call it differential amplifier with active load. That's how it's called. We can have a MOSFET amplifier, differential amplifier with P MOSFETs as loads. But when the P MOSFETs are connected like this, one of them has a short between its gate and its drain, Q3 has a short between its gate and its drain. And there's no V bias here. There's no DC voltage connected to this. It's just a short between gate and drain. That's it. We call this differential amplifier with active load to refer to this special configuration. And why is this? Why are we considering this? What is special about this is when we consider the regular differential amplifier and we take the output from one drain only, or in the case of the BJT from one collector only, I get 1/2 the gain. So I get half GMRD or half GMRC. And if I take the output differentially, I get double that. I get GMRC or GMRD. But to get double the gain for the previous cases, I had to take the output differentially. So the output cannot be between a node and ground. If I take the output differentially in the case of the previous MOSFET differential amplifier, if I take the output between drain 1 and drain 2, I get double the gain. If I take it between the drain and ground, I get 1/2 the gain, or I get half GMRC. And if I take it differentially, I get just GMRC. This circuit actually allows us to take the output between this drain of Q2 and Q4 to ground and get the full GMRC, not half GMRC. So this short circuit here, actually we can show using small signal analysis that it allows us to get the full gain of the amplifier even when I take the output between this node and ground. If I do this in the previous amplifier, I don't get the full gain, I get 1/2. For this circuit, we get the full gain. So the way to show that this is true is by doing small signal analysis over the whole circuit. And if I do small signal analysis, it's a multi-step procedure because I have to replace all the MOSFETs by their small signal models and do circuit analysis. There's no symmetry here to benefit from. There's it's actually it's just a circuit that where we can't recycle previous results, so we'd have to do a full small signal analysis. So it's kind of annoying. But if we do that, we can show the following. Assuming GMRO is much greater than 1, which is typically the case in MOSFETs. Not necessarily much bigger than 1, but maybe it's 20 to 50. So there is some error, a few percent error. Under this assumption, if GMRO is much larger than 1, then the differential gain would be GM RO2 parallel RO4, and there's no 1/2. So AD is VO divided by VID, VG1 minus VG2. So VO over VG1 minus VG2 would be GM RO2 parallel RO4, and there's no 1/2. We don't lose any gain if we take the output just from one drain, from one side. So that's kind of like twice the gain obtained from the previous differential amplifier with single-ended output due to this current mirror-like short circuit between gate and drain of Q3. Again, if we do small signal analysis and assume that the two inputs are equal, this will give me the ACM output over input when the two inputs are equal and the two inputs are both VICM. So VO over VICM, we can show from small signal analysis, it will be minus RO4 over 2 RSS. The output resistance of this is RSS times 1 plus GM3 RO3. Now this is much bigger than 1. We can neglect the 1. And RO3 and RO4 are typically equal. So we can say that this is approximately minus 1 over 2 GM3 RSS. So RSS is the output resistance of the current source I, and GM3 is the transconductance of Q3. This ACM is typically much less than 1 even. So the circuit would not amplify common mode signals, but we will see some output. And the output will be given by this expression, minus 1 over 2 GM3 RSS. Now, if RSS goes to infinity, as the current source becomes more ideal, ACM can go to 0. But even if it's not ideal, we get a small ACM and a large CMRR for this circuit. So this is the importance of the circuit, that we get a nice differential gain, the full differential gain that we can get, even if the output is taken single-endedly. without paying a big price in ACM. ACM is still decent, and in this case, decent means very small. This is the BJT version of this same circuit, and we have the same structure with Q1, Q2 being the differential pair, and Q3 and Q4 being the active load with this current mirror style short circuit between the base and the collector of Q3. Again, if we do small signal analysis, we can show that the gain is GM RON parallel ROP, and so that's AD. And ACM is minus RO4 divided by beta REE, and that's a pretty small ACM. It's not exactly zero. It will be exactly zero, or it will tend to zero if the current source is ideal. If the current source is not ideal and has an output resistance REE, then ACM is given by this expression. And where did we get these expressions? From full small signal circuit analysis of the whole thing. And notice that ACM is, if REE is of the order of small RO4, so if this is implemented by BJT, REE would be small RO of the BJT. And it will probably be comparable to RO4, say. And ACM would be then like 1 over beta. If beta is around 100, what would be ACM? It would be 0.01. So very small. While AD, maybe of the order of 100, 200, 500 maybe. So again, decent characteristics, large AD, very small ACM, and good CMRR. Now that we've seen the active loaded MOSFET differential amplifier, and we've seen the other implementations, we're familiar with the current mirrors and common source amplifiers, we can look at this circuit again, and now we should be able to identify all the subcircuits. So if you look now at the orange subcircuit, now we know what this is. The one that we've seen is not exactly this. It's not exactly this. This is the active loaded differential amplifier MOSFET version, but with the input MOSFETs being P and the active load being N. So it's like an inverted version of the one that we saw. So here, this is the current I. Q5 is implementing the current source I. These are the two input MOSFETs, so they're P. And this is the active load on the P MOSFETs Q3 and Q4 implemented using N. And that's perfectly fine. We can implement the active loaded differential amplifier using P MOSFETs at the inputs and N MOSFETs as active load. Q5 and Q8 are obviously a current mirror. Q5 is mirroring IRF to produce the current I. The current I is the current biasing the differential amplifier. The yellow sub-circuit is an active loaded common source amplifier. Q6 is a common source amplifier, but it doesn't have a simple RD between the output and the supply. It has a Q7. So the resistance here would be RO7, small RO7. This voltage is a DC voltage here. This is some DC voltage we bias. So there's no signal here, there's no signal here, and there's no signal here. This is obviously the supply, so there's no signal there. So that's why I see RO7 looking up, because there's no signal here at the supply, there's no signal here, and I see RO7 when looking into the drain of Q7. And for Q6, the input is at the gate and the output is at the drain. For the active loaded differential amplifier, we just derived some equations and we can use them. And now we can find the overall gain of this amplifier. So now we're looking at our first op-amp implementation. This circuit is something like this. This is 1, this is 2, this is 3. And of course, this is using a VDD and the minus VSS supplies. So that's what's inside this op-amp. This is a simple implementation of an operational amplifier. You may notice that there is this capacitor here that we're showing. We're not showing any other capacitor. There are other capacitors in the circuit that are due to the MOSFETs and due to the wiring. We're not showing them. I'm only showing CC. So this must be like an element that we're adding to the circuit. It's not parasitic. We are adding CC to the circuit. So what is this capacitor doing and why did we add it? This will bring us back to the discussion about the open loop gain of an op-amp and how we sacrifice it to stabilize the operational amplifier. We said that we introduce a pole at a very low frequency. And when we do that, the gain would drop starting this very small frequency. And that makes the op-amp stable. Okay, so we had to introduce a pole in the circuit. This is exactly what CC is doing. CC, this capacitor connected between the drain of Q2 and Q4 and the drain of Q6, so between the input and output of the common source amplifier. This capacitor CC is introducing a pole at a very low frequency to make the open loop gain of this op-amp. This is the body plot of the open loop gain. And it does something like this, starts to drop at some very low frequency. This is what CC is doing here. CC is added to the circuit by the circuit designers to introduce this pole at this very low frequency to stabilize the op-amp. And that's why we see it. And we don't see any other capacitor, even though there are other capacitors. There are capacitors all over the place here. But we show CC because it's an element that is added on purpose, and now we know why it's added to the circuit. So I can now find the gain of the first stage. I have formulas for all of these things. The gain of the first stage is minus GM1 RO2 parallel RO4. GM1 is equal to GM2, so either GM1 or GM2 minus GM1 RO2 parallel RO4. So this is the gain between the inputs. The inputs are here, and the output here. This is the output of the first stage. So A1 is the gain to the intermediate output at the stairs we see here. The second stage is a common source amplifier. And we know what is the gain of a common source amplifier, minus GM R prime L. So minus GM6, because Q6 is the amplifying MOSFET, R prime L is RO6 parallel RO7. The overall gain would be the multiplication of these two, because the common source does not load the differential amplifier. The input resistance of common source is infinite. So I just multiplied two gains. And this is the overall gain. It's like AD for the op amp. GM1, GM6, RO2 parallel RO4 times RO6 parallel RO7. So that may be of the order of like 1,000 or something like that. It's not very, very large. What about common mode gain? For the differential amplifier with active load, we have a formula. Minus 1 over 2 RO5, RO4 into divided by 1 plus GM3 RO3. That's the common mode gain. When the two inputs are equal, this is the signal that we see at the stairs between the two stages. Common source, when it sees this signal, it will amplify it. The common source doesn't understand differential or common mode or whatever. Whatever signal appears at the gate of Q6 will be amplified by Q6. So whether it's coming from equal inputs or different inputs, it will be amplified the same way. So the gain of the common source amplifier, when the two inputs of the op amp are equal, will be the same, minus GM6, RO6 parallel RO7, and ACM would be the product of these two quantities. So this is ACM for the op amp. And we can, of course, now find CMRR if we want to. CMRR would be 20 log AD over ACM. So that's an expression for CMRR in dB. So that's our op amp, and we now know what is AD for this and ACM. Of course, it's a very simple op amp. It's not ideal. AD is not infinite. ACM is not zero. It's a good start.